December 13th, 1916, Marmolada Massif, Dolomites. 4 meters of unbonded powder snow accumulate over 48 hours on slopes inclined between 30 and 45 degrees. The static friction coefficient of the existing base layer is exceeded. The cohesive strength of the snowpack drops below the shear stress applied by gravitational force. At 0600, the structural threshold is breached. The slope releases. The barricamenti of the Austro-Hungarian Alpine front were engineered for specific thermal and gravitational loads. Standard shelter design in 1916 included timber frames reinforced with local stone, positioned at elevations between 2,800 and 3,300 meters. Each structure was rated to withstand static snow loads of approximately 150 kilograms per square meter, based on average seasonal accumulation. Roof pitch was calculated to encourage passive shedding at angles between 35 and 40 degrees. Walls were double-layered with insulating air spaces. The structural beams, typically larch or spruce, measured 20 centimeters in diameter. Foundations were excavated into glacier ice or anchored to exposed bedrock. These shelters housed between 12 and 40 soldiers. They were spaced along ridgelines and glacial plateaus to avoid topographic funnels. The maximum rated wind speed was 120 kilometers per hour. No provisions existed in the engineering standards for dynamic impact loading from descending snow masses. A deep, low-pressure system moved southeast from the North Atlantic on December 10, 1916. It stalled over the Brenner Pass region. Moist air masses were forced upward against the Alpine barrier. Orographic lift intensified precipitation across the Marmolada group. Over the next 60 hours, snowfall occurred continuously. The snow-water equivalent measured approximately 400 millimeters. New snow density ranged from 50 to 80 kilograms per cubic meter. This produced a powder layer 4 meters deep. Surface temperatures remained between -8 and -12 degrees Celsius. Wind speeds reached 80 kilometers per hour, forming localized cornices and loading zones on leeward slopes. The existing base consisted of consolidated névé with density near 300 kilograms per cubic meter. No bonding occurred between the old surface and the new deposit. The temperature gradient within the snowpack was minimal. Metamorphism was arrested. By the morning of December 13th, the total overburden on slopes exceeded 320 kilograms per square meter. At approximately 0530 hours on December 13th, surface air temperature rose sharply. Radiative heating began as cloud cover dissipated. The temperature increase reached 6 degrees Celsius within 90 minutes. The coefficient of friction at the interface between old snow and new snow decreased. Shear strain exceeded the yield strength of the weak layer. The failure initiated on the Grand Paz slope at 3,200 meters elevation. The fracture line extended laterally across 600 meters. The crown face measured 4.2 meters in vertical height. The slab detached as a coherent mass. Initial velocity was governed by gravitational acceleration on a slope of 38 degrees. Within the first 3 seconds, the leading edge of the slab fragmented. The powder cloud preceding the dense flow reached speeds of 120 kilometers per hour. The entrainment of underlying snow increased the total mass by an estimated 30% during the first 200 meters of descent. The descending mass underwent granular fluidization. Interparticle collisions reduced internal cohesion. The flow transitioned from a sliding slab to a turbulent suspension. Velocity increased to an estimated 180 kilometers per hour. The depth of the flow ranged from 6 to 10 meters at the central axis. Air entrainment generated an overpressure wave traveling ahead of the main body. This precursor blast exerted dynamic pressures between 10 and 50 kilopascals. The powder fraction became aerosol-like. Visibility within the cloud dropped to 0. The path followed a natural drainage channel carved into the glacier. Total vertical descent measured 1,100 meters. The run-out distance extended to 2.3 kilometers from the crown. The duration of the primary event was approximately 90 seconds. The kinetic energy at impact was calculated post-event at over 200 megajoules based on mass and terminal velocity. Structures in the direct path were subjected to impact forces exceeding their design thresholds by factors between 50 and 100. Wooden beams fractured instantaneously. Stone walls were dislodged from foundations. Roof assemblies were stripped and entrained into the flow. Interior spaces were compressed and filled with compacted snow in under 2 seconds. The overpressure wave alone was sufficient to collapse lighter structures before the dense avalanche arrived. Shelters anchored to ice were sheared from their moorings. Those set into rock experienced complete burial under debris depths of 8 to 12 meters. No structural element survived intact within the primary impact zone. The debris field contained intermixed building material, equipment, and compacted snow with bulk density approaching 500 kilograms per cubic meter. Secondary smaller slides were triggered on adjacent slopes by the atmospheric disturbance. Total structural loss in the immediate area was recorded at 14 barracks and 3 observation posts. The teleferica network, composed of steel cables spanning distances up to 1,200 meters, was severed at multiple anchor points. These cable systems transported ammunition, food, and fuel to forward positions. The avalanche removed support pylons and tensioning mechanisms. Cable spans dropped into the debris field or were dragged downslope. The loss of this logistics corridor halted resupply operations. Forward units at elevations above 3,000 meters were isolated. Radio communication was intermittent due to atmospheric conditions and equipment limitations. Visual signaling was impossible during continued snowfall. The transport capacity of mule trains on remaining trails was insufficient to replace the teleferica tonnage. Fuel reserves at isolated posts were calculated at 4 days. Food reserves ranged from 7 to 10 days. The coupling of the avalanche event to the supply infrastructure transformed a localized geophysical failure into a theater-wide operational constraint. Alpine passes connecting the Marmolada positions to rear areas were blocked by deposits measuring 4 to 15 meters in depth. The compacted snow formed barriers with compressive strength near that of soft ice. The carved ice tunnels within the glacier, used for sheltered movement, experienced collapse where the overlying load exceeded structural limits. Tunnel sections were crushed or filled. Route networks that previously allowed traverse times of 90 minutes now required excavation efforts estimated at multiple days. Mechanical sleds and pack animals could not cross the debris fields. Soldiers on foot sank to depths of 1 meter in unconsolidated sections. Movement speed dropped to 200 meters per hour. Attempts to re-establish passage were hindered by ongoing instability. Wind-loaded slopes adjacent to cleared routes posed secondary release hazards. Mobility across the operational zone was reduced by an estimated 80% for a minimum of 72 hours. Excavation resources in December 1916 consisted of hand shovels and improvised wooden tools. Mechanical equipment was not deployed at altitudes above 2,500 meters. The debris compaction required cutting and levering rather than simple shoveling. Progress rates measured 2 to 3 cubic meters per man per hour under optimal conditions. Fatigue, cold, and hypoxia reduced efficiency by approximately 40%. The risk of secondary avalanches was elevated. Any disturbance of surrounding slopes could trigger further releases. Observers reported cracking sounds and snow settlement during recovery operations. Work was suspended multiple times due to weather deterioration. Visibility dropped below 50 meters. Wind speeds returned to 70 kilometers per hour. Additional snowfall of 30 centimeters occurred on December 14. The probability of locating and extracting individuals beneath 10 meters of compacted debris within a survival time frame was assessed as near zero. The estimated mass of the primary Grand Pas avalanche was 120,000 metric tons. The debris field covered an area of 18 hectares. Maximum deposit depth reached 14 meters. The count of destroyed structures across the Marmolada sector totaled 47 barracks, 12 observation posts, 8 supply depots, and 6 medical stations. The number of personnel unaccounted for in the immediate aftermath was 332. Secondary avalanches triggered on December 13 across the broader Dolomite front added an additional 68 structures to the loss inventory. The combined avalanche events of December 13, 1916, later designated White Friday, resulted in infrastructure collapse across 14 separate mountain positions. The cumulative debris volume was estimated at 4 million cubic meters. The snow-water equivalent represented a localized precipitation anomaly 3 times the historical December mean. Austro-Hungarian military disaster logs recorded the event as a geophysical anomaly compounded by meteorological extremes and the tactical necessity of high-altitude occupation. Post-war analysis by Alpine researchers in the 1920s identified the December 1916 event as foundational to the development of avalanche science. The Swiss Federal Institute for Snow and Avalanche Research formalized the study of snowpack mechanics in 1931. Classification systems for avalanche type, trigger, and runout were derived in part from forensic study of White Friday debris fields. Modern nivological practice includes snow profile analysis, shear frame testing, and weather-driven hazard forecasting. Current structural codes for alpine construction mandate dynamic load factors for avalanche-prone zones. The 1916 Marmolada failure remains a reference case in the engineering of mountain infrastructure and the understanding of coupled natural and human system vulnerabilities.